Johnny here with Simpson Math. In this video, we're going to be talking about right triangle trig. That is, we're going to be dealing with right triangles, and when given some pieces of information, we can calculate other pieces of information. So if I know maybe the length of one side of a triangle and one of the angles, I can then go off and maybe calculate another side length of that triangle. We've all maybe seen this type of problem before. Maybe pretend that this triangle represents the height of a tree. So this line down here, the base, is the ground, and you've got this green tree which just happens to grow straight up, and you're down here on the ground, and you're able to measure the distance you are away from the tree. And maybe you have some sort of protractor, so you're able to measure this angle down here, the angle from the ground to the height of the tree. Given that information, we can calculate the height of the tree, and maybe even the hypotenuse, and maybe even other angles. That's right triangle trig. You know some information, and you use that information using trigonometry to fill out the rest of the triangle, to solve the triangle. That's kind of the goal for this lecture. Now, before I continue, I must say, stop. Do not watch this video. If you found this video randomly on the internet, just stop watching it. This SOHCAHTOA stuff is nonsense. If you are one of my, or just instead, go watch my video where I define the trig functions. Trig Defined. Find that video. If you're one of my students and you've come across this video, make sure you have watched the Trig Defined video first. It is prerequisite knowledge. You must know the definition of the trig functions before this video. Again, let's say you were doing the homework from that lecture and you had to ask me a question. Stop this video right now, go back, rewatch that trig definition video, and rework that homework 2 more times. If you worked that homework, but your answer didn't quite match your friends or classmates, or you're still having doubts about this class, stop this video right now. Go watch the Trig Defined video. I'm not a fan of SOHCAHTOA. I'm not a fan. Oftentimes, every semester, students come to me in trigonometry or in pre-calculus, and they've been told, or then they've been taught this SOHCAHTOA definition, which I have to admit is quite cute. And they can solve triangles. They get it. They understand how to solve triangles. But the SOHCAHTOA definition acts as a ceiling to so many students. So they understand the SOHCAHTOA definition of trig, but then they're stuck in this developmental, lower level understanding of trig. The true definition of trig deals with x values, y values, the radius of a circle, and we're talking about standard position, the Cartesian plane. That is how you define trig, and that is how you solve right triangles. This SOHCAHTOA definition is lower level thinking. If you're stuck down here, that's okay, but go back. Make sure you completely understand that definition first. Oftentimes, I have to sit one-on-one with students who learn SOHCAHTOA first, and it's really hard to break apart that ceiling, break apart that understanding to really teach them the trig, this whole field of study. So SOHCAHTOA, it's just a easy way to think about the definition. What I mean. Okay. Let's say I've got this triangle, and I know some of the information. Well, trig is defined as x, y, r, and a reference angle. So I must know what angle is the reference angle. So let's go ahead and label the reference angle. Maybe it's this high angle up here. Oh, jeez. I'm going to label this angle theta. Now, what does that mean? That means I'm supposed to start on the Cartesian plane. Here I've drawn one out. I'm supposed to start on the positive x-axis, 0 degrees. And I'm supposed to start going counterclockwise to create a positive angle. And I'm going to stop as soon as I get to that angle. So I'm tick, 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 plop. There I've got my vertex at the origin. I have my terminal ray pointing off into quadrant 1. And theta, the reference angle, is in quadrant 1. Now I feel comfortable talking about trig. I have an x value for this triangle, which is the base in this position. I have a y value, which is acting as this height. And I have the radius, which is acting as this hypotenuse. That's different from if I chose maybe the bigger angle to be theta. All of a sudden, my terminal side is pointing way up here, and I've got a different x and a different y. So it all depends on which angle is that reference angle. Let me go back to the one we started with. Okay. So I have to admit, though, once we get the triangle in a standard position, if I asked you to find sine of theta, well, hopefully you would use the definition and you would use the y value over the radius. But I can admit it may be easier to call this the opposite side length and the hypotenuse, as opposed to y and r. Maybe you want to call this opposite over hypotenuse. I'm going to give this name, I'm going to call this B. I'm going to call this C, and I'm going to call this side length A. Sine of theta, sine of angle theta, can be thought of as the opposite side length over the hypotenuse. Opposite over hypotenuse. In this triangle, that would be the B value over the C value. This is where the SO comes from SOHCAHTOA. Sine is defined as opposite over hypotenuse. Sine, opposite, hypotenuse. So, if you know sine, then you know the reciprocal function, cosecant. Cosecant of theta is just going to be the reciprocal, the hypotenuse over the opposite. For this triangle, that would be C over B. Now, cosine. The true definition of cosine is the x value over the radius. So that would be A over C. We can call that, though, maybe the adjacent side length. Opposite meaning it's the side length opposite the angle, so it's not touching. Whereas A, this side length, is touching the reference angle. It's adjacent to it. Like your neighbor is adjacent to your property. A is adjacent to theta. Cosine is x over r from that true definition, but we can call it the adjacent over hypotenuse. And as an example, that's A over C with this triangle. Well, if you know cosine, then you know the reciprocal function secant. Secant of angle theta is defined as the hypotenuse over the adjacent. The reciprocal, C over A. Tangent, normally defined as y over x. In this terminology, we have opposite over adjacent. Or B over A. Cotangent of theta would be the reciprocal, the adjacent over the opposite side length. With this example triangle, that would be A over B. So these letters are very specific to the situation we're dealing with. The SOHCAHTOA definition is all about opposites, adjacents, and hypotenuses. And it is convenient. If I start to talk about this triangle, I know that no matter how I turn it, when I measure B, it's going to have a positive measurement. When I measure A, it's going to have a positive measurement, and the hypotenuse will have a positive measurement. So if I'm measuring trees, if I'm measuring the width of a river, if I'm doing some sort of construction project, we're talking about positive numbers. So these are always going to be triangles that are in quadrant 1 when they're put in that standard position. So the y's and the x's and the r's are all positive. So we can think about it as in this SOHCAHTOA definition. Let's jump straight into an example and I'll show you how cute this is. I'll give you some information. Let's use the given trig function. Something like cotangent of theta is 6 over 11 to find the other 5 trig functions. We've done problems similar to this. Like we did some where I gave you a coordinate and you have to go off and find the other 6 trig functions. This is very similar to that. This time I've been given cotangent of theta is 6 over 11. Okay, and I want to find the other 5. Okay. Now, if I don't have any other information, like in the past, I would tell you cotangent is 6 over 11, but we also know one more stipulation. Sine is negative. And so we had to discern which quadrant we were in. This problem is much more simpler because all I've given you is this one piece of information. So we're just relaxing here. We're not confined to the Cartesian plane. We're just talking about a triangle, a right triangle. So my first step is to draw a right triangle. The second step is to determine where that reference angle is. I'm going to put it somewhere different just to help solidify this right triangle trig or this SOHCAHTOA definition. I'm going to put the angle here. Meaning, if I needed to put this in standard position, I would have to do, something clever. I'd have to pick it up and either talk about this as a negative angle or turn my page like this. Hopefully you can see that. And talk about the triangle like this. But I'm pretending, or I'm saying that we can be more relaxed. I've got a right triangle. First step, draw it. Second step, I've got to determine what angle we're talking about. And we get to decide where to put that theta. Then I need to determine where to put this 6 and where to put this 11. Well, cotangent is the reciprocal of tangent. TOA is in the SOHCAHTOA definition. Tangent is defined as opposite over adjacent. TOA. So the reciprocal cotangent would just be the adjacent over the opposite. So looking at this angle, the adjacent would be the 6. That is, 6 is touching
Here's the top search result.
The theta. O, the opposite, is the denominator. So the side length opposite theta is 11. Now, I did not call this side length 6. I did not call this one the adjacent one, because even though it is touching the reference angle, or this theta, it's clearly the hypotenuse. This is the side length opposite the 90-degree angle, so that's reserved for the hypotenuse. So if that's theta, this is the adjacent, this is the opposite. Cotangent is defined as adjacent over opposite, 6/11. Now I can use Pythag to find the hypotenuse. In a previous lecture, I might have called that r, the radius, but I'm just calling it h this time for hypotenuse. These numbers don't look familiar to me, but I at least can do the math. 6 squared is 36, 11 squared is that 121. I need to sum those together, 157. You look for factors of 157 when you're trying to simplify the radical. I can't think of any right off the bat, so I'm going to leave it as the square root of 157. That's my hypotenuse. So I can now answer all 6 of the trig functions. Sine of theta is defined as opposite over hypotenuse. So SOH, opposite over hypotenuse. Clean that up. It has a reciprocal function, cosecant. I'm not going to reciprocate this form because that would put a radical back in the denominator. I'll simply put the hypotenuse over the opposite and call it a day. And of course, if we know cotangent, we know tangent. Tangent is defined as opposite over adjacent, TOA. So opposite 11 over adjacent 6. Cosine is adjacent over hypotenuse. So we're talking 6 over the square root of 157, which needs to be cleaned up. 6 roots of 157 over 157. And if you can tell me cosine, then secant should follow right beside it as the root of 157 all over 6. Okay. SOHCAHTOA. Nice and relaxed. I think I'm going to play around. Remember what I mean by play around? If not, we've talked about this in previous videos. I'm going to draw a right triangle. I'm going to label it this time ABC. And using the Socatella definition, with my theta sitting right there, what is sine of theta? Socatella, opposite over hypotenuse, A over C. All right. Well, that's fun. Looking back at my triangle, I've got a 90 angle there. This is theta. How could I calculate this other angle? Like, let's say theta was 30 degrees. How big is the red angle? Well, 60, right? Because if this angle measures 90 and there's a triangle has 180 degrees altogether, well, there's only 90 remaining in these two angles. So if this angle is 30, then the red angle is 90 minus 30, 60. If theta is 15 degrees, then the red angle, 90 minus 15, 75 degrees. So I'm going to call this red angle 90 degrees minus theta. Or because this is trigonometry, you may want to call that pi halves minus theta. But 90 degrees minus theta should be the measurement of this other angle. I'm calling that angle, the red angle, 90 degrees minus theta. So now I have a new question for you. What is cosine of 90 degrees minus theta? All right, we're in Socatella definition. Cosine is adjacent over hypotenuse. We're in Socatella definition. The angle is very important. We're not talking about this black theta anymore. The adjacent to theta is b, but we're not talking about that angle. We're talking about the red angle. Cosine of the red angle. Well, the adjacent has flipped. The adjacent to the red angle is now this side length a. The hypotenuse, though, is going to stay the same. The hypotenuse is always going to be this c. What do you notice about sine of theta and cosine of 90 minus theta? Well, they equal the same thing. We call this a co-relationship or cofunction. Sine has a cosine. When we first introduced the trig functions to you, we said, oh, sine goes really well with cosecant because they are reciprocal functions. But sine and cosine have this relationship. And I'm about to write down some more identities. In previous videos, we've talked about quotient identities and reciprocal identities. I'm now going to give you 6 more identities, and these are called cofunction identities. Now is probably a really good time to, this is the lecture notes over Right Triangle Trig. So you don't want to break this up, but you might want to bring out another sheet of paper, and maybe at the top of that paper you write trigonometric identities, and you start to list all the identities that we've learned so far. So quotient, there's 2 of those. Reciprocal, there's 6 of those. And now cofunction, there's 6 of these. So we're making a list that just seems to be getting longer and longer. So I'm going to put them here in this lecture, but you may want to start making like index cards or some sort of like cheat sheet, getting them like organized, your notes. All right, sine of theta is always equal to cosine of 90 minus theta. That's always going to be true. And it goes the other direction. Cosine of an angle is equal to sine of 90 degrees minus theta. Oh, I just realized I don't have a nice unit circle on me, but I would love to show that. Where did I put it? I have an ugly one. Bear with me. Yeah. This one has seen a semester or 2 of love. So let me do this triangle one more time. We just said this first identity. The second one is also true. So if I asked you for cosine of theta, SOHCAHTOA, cosine is adjacent over hypotenuse. So cosine of theta would be b over c. B over c. Sine of 90 minus theta. This is referring to the other angle. Sine of this other angle is opposite over hypotenuse, But notice they both end up as b over c. Always true. If I switch over to the unit circle, man, this is too much going on. Let me scratch that. I'll talk about that in a different video. All right, there's some more of these. Because secant, the secant function has a cosecant. And this relationship holds true there as well. And we can write this in the other direction. Cosecant of theta is always going to be equal to its cofunction secant of 90 degrees minus theta. Tangent has a cotangent, and cotangent has a tangent. And I'm just writing this pi halves minus theta. You may see pi halves minus theta. It's the same idea. That angle that measures 90 degrees or pi halves or in standard position is pointing straight up. That is cofunction identities. Sine has a cosine, secant has a cosecant, and tangent has a cotangent. All right, that was me playing around using the Socatella definition to come up with this interesting, cool thing. I'll talk about the cofunctions more when we get to graphs. All right, let's do another problem, though. Use the fact that cosine is 1/4 to find, let's say, part A, secant theta, part B, let's do sine theta, part C, tangent theta, and part D, cotangent of 90 degrees minus theta. Now is a good time to pause the video and see if you can work this problem on your own. Me, when I first see this problem, I am only given a cosine value. I'm not being restricted into other quadrants. If they did not say cosine is 1/4 and sine is negative, like that's not worrisome to me. So this is just that SOHCAHTOA, super relaxed. And because of that, I'm going to draw a right triangle. And you get to decide where that right angle is. It's got to be perpendicular. And you get to decide where that reference angle is. Last time I drew it up there. This time I'll draw it down here. But that's super important. All right. Now, cosine, SOHCAHTOA, is adjacent over hypotenuse. So this is the adjacent over the hypotenuse. So my adjacent better be 1 and my hypotenuse better be 4. Secant is defined as the hypotenuse over the adjacent, or the reciprocal, 4. Easy peasy. Sine is defined as opposite over hypotenuse. So for sine and for tangent, I'm going to need this opposite side length. But we're pros at the Pythagorean theorem. It says you take the side lengths and square them. That's O for opposite, not 0. Square them, sum them, and that's going to be the hypotenuse squared. Solve for O squared. Take the square root of both sides. The square root of 15, I could bust up 15 into 5 and 3, but those are not perfect squares. So I'm just going to leave the opposite side length as the square root of 15. And now I'm able to answer the sine. Sine is opposite over hypotenuse. The root of 15 over 4. Tangent, opposite over adjacent, root 15 over 1, but anything divided by 1 is just itself. So I'm just going to say root 15. Part D, cotangent of not theta. We're not talking about this angle anymore. We're talking about some other angle. Where is that angle? I don't see that angle. Oh, yeah. If this angle measures theta, then the other angle would measure 90 degrees minus theta. So we're talking about a new angle here. To that angle, cotangent is defined as the adjacent over opposite. The adjacent to that angle is root 15, and the opposite is 1. Oh, the same thing. Oh, cofunction. Oh, tangent and cotangent of 90 minus theta, those are the same thing. That's that little identity we just kind of talked about. Cotangent and tangent 90 minus theta, or more specifically, tangent and cotangent of 90 minus theta are the same thing. They are equal to each other. So if you know tangent of theta, then you know cotangent of 90 minus theta. This is a cofunction identity. It'll be very handy to know those identities. But if you don't, notice I solved it by just using the SOHCAHTOA definition and knowing that's my other angle out there. All right, I'm going to play around some more. This SOHCAHTOA stuff is so easy. I feel like I can just come up with stuff. I'm going to come up with new identities and new rules. Let's see. I'm playing around. I'm going to draw that same right triangle from before. A, B, C. I'll put theta in the same place. So I'm starting off the same as the last time I played around. I'm drawing that same ABC triangle. And I know that that Pythagorean theorem is always true for right triangles. So I'm going to play around with it. Just playing. Cool. Nice. Nice little equation we're all familiar with. Let's see. If I asked you if it was legal, like, can I multiply everything by 5? Is that a legal move? Because of the equal sign, sure, you can multiply the right-hand side of the equation by 5, as long as you do it to the left-hand side as well. You can distribute and multiply everything by 5. It would be an equal statement. Can I divide everything by 5? Well, sure, division by 5, you can think of it as multiplication. You're multiplying by 1 over 5 or a fifth by everything. And that's totally legal as long as you're not trying to divide by something weird like 0. But yeah, if you can divide by any number on the right-hand side as long as you do it to the left-hand side. Well, okay, that sounds fun. I like this. In fact, what if I were to divide by c squared? I can divide by any number. You just told me so. So if I divide the right-hand side, c squared divided by c squared, would that just turn into a 1? Okay, let's just see. That seems legal. You know, c can't be 0, but if I'm talking about the hypotenuse of a triangle, surely it's not 0. And then I think we're all on board with saying anything divided by itself is just 1. And on the left, if you have a numerator squared and a denominator squared, you can rewrite that. Like if that's 9, let me just write it down. You can rewrite that as the fraction being squared. If I had a over c squared, that's a over c times a over c, which is just a squared over c squared. I'm going to just rewrite these using that old exponent definition or property. Now, a over c, that sure does look familiar. A over c. A over c. What in the world is a over c? Well, it's a ratio of side lengths. So that sounds like the output of a trig function. What trig function to this theta would spit out a over c, or the opposite side length over the hypotenuse? I'm thinking sine. This a over c, that's just a fancy way of saying sine of theta. If I asked you for sine of theta, you would tell me, like you did earlier, sine of theta is a over c. So if you have a over c, you can call it sine of theta. What about b over c? Can I do something similar? Adjacent over hypotenuse? Wouldn't that be cosine? Cosine theta being squared. Okay, this is looking really cool. Now this may be some new notation for you. If you have a trig function and it's being raised to a power, we don't write the power out there. We have a new notation for that. We call this sine squared theta plus cosine squared theta equals 1. These exponents, though, they just mean you need to find the sine value and then square it. You may have done something similar with logarithms. Typically, you don't do too much of it in a college algebra setting, but you may have. If you have the natural log of x and you multiply it by the natural log of x, that's the natural log of x squared. But we call that ln squared of x. So it's just this weird notation, or it's the notation we use. It's to help us not get confused about where that square is, because it is not equal to the natural log of x squared. So it's not equal to sine of theta squared. The square is not on the theta. The square is on the sine function itself. All right. But this relationship right here, that's really cool. We're going to be using this relationship a lot. Now this came from just playing around with the Pythagorean identity. So we call this the Pythagorean theorem. So we call this the Pythagorean identity. Oh yeah, didn't I just mention now maybe a good time to start up, separate from the notes, some sort of identity list, like a cheat sheet? Because we just added 6 cofunction, now I'm going to add some Pythagoreans as well. So we call this the Pythagorean identity. All right. Now, I'd like to maybe play around with this for a little bit. All right, so if I have an equation, we said earlier, it's legal to just divide by stuff. I can divide everything in that equation by any number I want to, except 0. But any number. So, and in fact, last time I divided by c, and I chose c because that was a nice little 1. It was easy to divide. I think I'm going to do that again. I'm going to divide by sine squared. Sine squared divided by itself would give me another cool little 1. I can divide the right-hand side of the equation as long as I do it to the left as well, dividing everything. Oh, whoa, okay, I see a lot of cool things. But let's start with this one. Sine squared divided by itself is going to be a cool looking 1. Now, cosine squared over sine squared, that should look somewhat familiar. Ignore the squares for just a little bit, because those may be new to us. But if I said, what is cosine over sine? Well, remember from a previous lecture, we had quotient identities. QIDs for quotient identities. And we said that cosine of theta divided by sine of theta is the same thing as cotangent theta. Remember that? If not, go back to that video and rewatch the part where we talked about deriving the quotient identities. But I claim I've got that idea. This cosine over sine is cotangent. Now the squares may confuse you, but if you had cosine over sine times cosine over sine, and you were to multiply that out, you'd have cosine squared up top and sine squared down below. And each of these you can turn into a cotangent. This is a cotangent. This is a cotangent. So when you multiply it, you would get a cotangent squared. So I'm just using the quotient ID right here. You can think of it as using it twice, but I'm just going through and saying, hey, I know that this is going to be a cotangent squared theta. And what's 1 over sine? It's in your notes. Or another way to, when someone says what is 1 over something, that's another way of asking, what is the reciprocal of sine? Well, you know that. The reciprocal of sine is cosecant. So if I have 1 over sine and 1 over sine, I'm going to have 1 over cosecant and 1 over cosecant, or basically just cosecant squared. Or I said 1 over cosecant, I didn't mean that. This is just cosecant squared. This is just another Pythagorean identity. It comes from this. We derived it from that. Let's do that again. That was a lot of fun. I'm going to take this main Pythagorean identity, and this time I'm going to divide by something different. Last time I divided by sine to get 1. This time I'm going to divide by cosine squared to get 1. And I'm having a lot of fun here. What is sine over cosine? That's just tangent. In this case, tangent squared. Cosine squared divided by itself is 1. 1 over cosine, or reciprocal of cosine. Well, that's just secant squared. I'm going to kind of organize this a little bit better. There are 3 of these Pythagorean identities that we need to be very comfortable with and familiar with and have memorized, basically. I claim if you can just memorize the first one, the fact that sine squared plus cosine squared equals 1, then you can derive the other two like we just did. 1 plus cotangent squared equals cosecant squared. Tangent squared plus 1 is secant squared. If you're sitting down and trying to come up with patterns to help you memorize, you can notice that the reciprocal functions are kind of off on their own. The tangent and cotangent, those kind of go well together. They're the things that are being added to 1. And the co's go together. Cotangent goes with cosecant. Tangent is not a cotangent, and secant is not co. All right, put those 3 in your notes. Put them on a identity cheat sheet or list. Let's go back to some right triangle trig questions. Let's say you're trying to do something in the real world. So maybe you're trying to measure the width of a river. So let's see. And you've got some fancy tools to help you get some of the measurements. So you start here and you lay down a rope headed east and west, I suppose. Somehow it's, perfectly straight. And your rope measures 10 feet. And you've got something on the other side, like straight across. So maybe you start here and you're looking at the other side of the river, and you have a friend over here that's helping you set this up. So here's your friend. And she's helping you out. All right. So that's forming, of course, a perfect perpendicular line, or a 90-degree angle. And you're able to stake this rope into the ground. You measure off 10 feet, and then you look at the angle you are away from your friend, and you've got some handy-dandy protractor, so you're able to measure this angle. So you're forming a right triangle. And your protractor tells you that this kind of looks like maybe 62 degrees. And you're really concerned with the width of the river. Maybe I have no idea why you're doing this. Maybe you need to build a bridge. I have no idea. Okay. But you want to determine the width of this river. I think with just those 2 pieces of information, we're able to calculate W, the width of the river. All right. This is a common type of problem with this right triangle trig, where you're given a triangle, you're given some of the information, and you're asked to find at least one piece of that triangle, if not all. Any bright ideas? Yes, what are you thinking? Well, this isn't that SOHCAHTOA feel, we're just being relaxed. So it's with SOHCAHTOA, we need a right triangle, check mark. We need an angle, check mark. So then what trig function would maybe talk about the width and this side length of 10, the information that we know about and the one that we're after. So to me, this is the adjacent and the opposite. Well, TOA does that. Tangent of this angle. This angle we know is 62 degrees. It is equal to the opposite side length, the width, divided by the adjacent side length, 10. If you want to solve for the width, you simply need to take that equation, multiply both sides by 10. I'm done. This is the answer to the question. This is the width of the river. We call this an exact value. If I really was building a bridge, I would want to be as exact as possible. I do not want to round too early because that bridge may, if I do some rounding errors, and then we're all dead. But here we go. I've got the width of the river is 10 being multiplied by the tangent value of 62 degrees. Now, if you're wanting to check yourself, or you want a good decimal approximation, like looking at my triangle, if this measures 10, then this better be longer than 10. This looks way bigger than 10. So we can use maybe some technology, a calculator, or like a Desmos on the website to get a decimal approximation. Another way to approximate is with the unit circle. So I'm about to bust out a calculator, but here's another skill that we should maybe start to practice. Because 62 degrees is not on the unit circle, but it's very close to an angle that is on the unit circle, 60 degrees. I'm going to draw the first quadrant. I'm going to draw the 60-degree angle. This has a coordinate, some cosine value, some x value, and some sine value, some y value. At this point in the class, I'm wanting you to have those points memorized. So if I said, what is cosine of 60 degrees? That's this x value. You should have that memorized as 1/2. And it's positive because we're in quadrant 1. The sine value is the height, or the y value. It's much longer than 0.5. It's, yes, you know this. What is sine of 60 degrees? Or maybe if you're more comfortable with radians, this is pi thirds. So what is sine of pi thirds? Yes, it's in your notes. You have this memorized already. This is the square root of 3 over 2. Now, tangent values, I kind of also want you to maybe have memorized, but if you're not there yet, that's okay. So let's find tangent of 60 degrees. Tangent, remember, is defined a couple ways. It's y over x, or like we said earlier, it's just going to be sine over cosine. So I'm going to take the sine value, root 3 over 2, and divide by the cosine value, 1/2. And we all maybe divide by fractions a little bit differently. Some of you may want to keep, change, flip. I'm going to multiply, though, by a fancy 1. I'm trying to get rid of these denominators in the fraction, so that 2, I can kill those off by multiplying by 2 over 2. It's going straight across. Root 3 over 2 times 2, the 2's will reduce, leaving me with root 3. In the denominator, 1/2 times 2, The 2's reduce, leaving me with 1. Oh yeah, anything divided by 1 is just itself. So tangent, I know I put theta there, but I'm talking about 60 degrees right now. Tangent of 60 degrees is simply the square root of 3. The square root of 3 we know is between 1 and 2. So the square root of 1 is 1. The square root of 4 is 2. So the square root of 2 and the square root of 3, those are between 1 and 2. Root 3 is a little bit bigger. I have it memorized at about 1.7, somewhere in there. I'm going to put these approximately equal to, because I'm about to approximate this as a decimal. It's about, yeah, 1.7-ish. Okay, I'm doing all this because if I know tangent of 60 degrees is about 1.7, then tangent of 62 should be close. I acknowledge it may be a gross estimate, it may be way off, but tangent of 62 is about 1.7. If you take 1.7 and multiply by 10, doesn't that just move the decimal place over 1? Wouldn't that just make this 17? Is 17 a good estimate for this width? If this side length is 10, doesn't that kind of look like maybe it could be 17? So this estimation process using the common angles we're familiar with on the unit circle, this is a skill I'd like you to start practicing. And now is a really good time with these right triangle trigs. If any of these angles are close to 30, 45, 60, 90, any one of those, try to estimate first. But I'm with you. All of y'all are saying, oh my dear, please let's just use a calculator. So I'm going to shove this into a calculator. Now, as soon as I use technology to get a decimal approximation, we're no longer talking about exact values. This is an approximation. So I'm going to use these wavy symbols to say the width is approximately equal to. You can use your phone calculator. You can use an old school calculator. You can use the internet like Google or Desmos, Wolfram Alpha, anything. But a common thing to worry about when dealing with trig is you have to tell the computer if you're dealing with radians or degrees. Sorry about the glare. But you can see that this TI has rad down here. So right now it's in radian mode. I need to get out of that because the angle I'm dealing with is in degrees. So for mine, I just type on, I guess this is a degree symbol. Yep. Hit the arrow, say enter. So for your calculator, you may have to change the mode. You may have to figure that out. It's different for every calculator. But now that I'm in degrees, I'm going to just type this in. 10 times tangent. Notice it opens up the parentheses. It's saying of what angle. I'm going to type 62 degrees, or 62, and close off the argument of tangent. 18.8. You know, I'm really happy with my estimation of 17. Pretty good. In fact, maybe root 3 is closer to 1.8 than I think it is. So I'm happy with this. So 10 times tangent of 62 is 18.8-ish. All right. So that's an example of like a real world problem. Now it's not going to be as pretty as this. Of course, you can't lay a flat piece of rope, but you understand the idea. We're just getting some estimations. We can use these right triangles to set up trig functions. That's the main idea. setting up a trig function using the Socatella definition to quickly solve for the missing piece. All right. Now I'm just going to play around with some crazy looking problems. No longer with right triangle trig. I guess we're still there. Here's an example. Let's say we know sine theta is equal to m squared minus, that's a 2, m squared minus n squared over m squared plus n squared. And we're asked to find tangent of theta plus secant of theta. Whoa, okay, we switched gears really fast. Like, this is, really it's the same problem, but we went from this nice little happy world where triangles make sense to us to a lot of algebra, but that's okay. We're still in this relaxed, super chill SOHCAHTOA world. And they just told us something really important. Sine of an angle is this ratio. Don't let the m's and n's scare you just yet. Remember, sine is just the opposite over the hypotenuse. So I'm looking at the opposite and I'm looking at the hypotenuse. SOHCAHTOA. So again, someone says trig function, you should instantly start thinking about right triangles. I'm going to draw a right triangle. As soon as you have a right triangle, you need to worry about that reference angle. Is it this angle over here? Is it this angle over here? Well, you're creating this problem, so you can decide where that theta is. I'm going to put it down here. Sine, opposite over hypotenuse. I can label my triangle. I know that my hypotenuse is sitting across from the right angle, so that m squared plus n squared better be the hypotenuse. And then the difference, m squared minus n squared, has got to be opposite that reference angle. Okay. Now it asks for tangent plus secant. Let me think about that for 2 seconds. If someone asked me for tangent plus secant in the SOHCAHTOA world, I would be thinking, oh, well, they mean the opposite over adjacent plus, let's see, that's the reciprocal of cosine. Cosine is the ka, adjacent over hypotenuse. So this must be the hypotenuse over adjacent. I know the opposite, I know the hypotenuse, but both of these have a denominator that's the adjacent side length. So it does look like I'm going to have to go off and find that adjacent. How do we do that? With our best friend, Pythagoras. I'll call this A for adjacent. The Pythagorean theorem says the side lengths squared and summed so that's the adjacent squared plus the opposite squared will be equal to, and I'm running out of room, I should have done this down there. Equals to the hypotenuse squared. Okay, I know how to expand binomials. So if I have ilm squared minus n squared. There's just two of them sitting there side by side. That's all the exponent of 2 out here means. I just have the opposite times the opposite squared. And I can expand this out. You may want to call that FOIL. It's just massive distribution. So ilm squared times ilm squared is ilm to the 4th. Then I'm going to have a minus ilm squared n squared minus ilm squared n squared plus n to the 4th. Similarly over here, if you need to write it out side by side so you can do your little fingers, have at it. First, outer, inner, last. Ilm to the 4th plus ilm squared n squared plus ilm squared n squared plus n to the 4th. I still almost ran out of room. I see like terms. These are the same thing. These are the same thing. They'll add together. It looks really scary, but something cool is about to happen. If I take ilm to the 4th and I try to subtract it over to the other side of the equation to combine it with that like term, well, they're just going to cancel each other out. If I subtract ilm to the 4th power from both sides, they're gone. Same thing with my n to the 4ths. If I try to move it over, they're going to cancel each other out. Now these are like terms, but they're not going to cancel each other out. I think I'll move this one to the right-hand side just to avoid any negativity. You should always remove negativity from your life. So I'm going to add this over. I should have 4 of those in the end. All right, now what am I trying to do? I am trying to, find a. So a would be the square root of this. Now that I've isolated the a squared, like it's all by itself on its side of the equation, I feel comfortable taking the square root of both sides of the equation. And the square root of a product, you can do each factor independently. The square root of 4 is 2. The square root of ilm squared is ilm. The square root of n squared is n. My adjacent side length is 2 ilm n. I can go put that on my triangle. The adjacent is 2 times ilm times n. And I think I'm ready to continue with that sum that they gave us. Tangent plus secant is defined this way using SOHCAHTOA, and I have all these values. This is, where did my black pen go? This is ilm squared minus n squared over the adjacent 2 ilm n. To that, I need to be adding this other fraction, which is the hypotenuse, ilm squared plus n squared over the adjacent again, 2 ilm n. Oh, thank you, Mr. Simpson, for giving me at least a common denominator, so that when I add these two fractions together, the common denominator will stay the same. Oh, and these are like terms. Ilm squared plus ilm squared is 2 ilm squared, and the n's will cancel each other out. Okay, well, I can do some more simplification. The 2's can reduce. One of these ilms can reduce. That's a slash through mark with a twirl at the end. So I'm left with 1 ilm over 1 in as the sum. Yeah, that's pretty cool. That's fun. So it looks scary. There's some algebra that's coming back with a vengeance, but it's just they gave you the sign value, opposite over hypotenuse. They asked you for some tangent value and a secant value. Well, that's opposite over adjacent and the hypotenuse over adjacent. And then they want you to sum them together. Okay, do it. That's not that bad. Let's do one more hard one like that. This is as hard as I can make them. So if you feel comfortable, then you're doing good. And if you're scared, don't worry about it. Practice the homework, it'll be fine. Let's try something like this. All right, they give us this equation. They also give us a triangle. So let me draw this triangle real quick. It is definitely a right triangle. I'm making it a little bigger because there's something inside of the right triangle. And we've got 2 angles. This first letter, that's the Greek letter alpha, the first letter of the Greek alphabet. That's alpha, and that is this angle right here. This fancy looking B is beta, and that represents this angle here. Theta is also a Greek letter. We commonly use theta, but instead of theta, I'm using alpha and beta. And the height of this triangle is h. And we do not know the base of this triangle, but we do know that this first piece measures d units, and we know that the second piece measures x units. Okay, this is quite funky, but hopefully you see a right triangle like normal with a reference angle of alpha. And then hopefully you see this other right triangle with reference angle beta. And they just happen to be using the same right angle. Cool. And they ask us to show or somehow prove or just make sure this equation holds true that h, the height of this thing, is equal to d divided by cotangent of this angle minus cotangent of this second angle. When you write minus signs, you want to give them their proper due. They deserve more respect than we give them credit. Same with these equal signs. You don't want them to bleed into the division symbol. You don't want them to be lost. Make them nice and bold. Okay, I'm going to do a little bit at a time. That looks really scary to me, so I'm going to focus in on just cotangent alpha. And I'll do it in green. Cotangent alpha. Well, cotangent is the reciprocal of tangent, and we have the SOHCAHTOA definition sitting right here. Tangent is opposite over adjacent. So as soon as you mention alpha, we're talking about this triangle here, ignoring the B part. I've got this big triangle with an alpha right triangle. Now, if I want cotangent, then I need the adjacent, which is all of this, over the opposite, which is h. I don't know what all of this is. But if this part is d and this part is x, what could I call all of it together? Like if this is 2 and this is 3, I would just simply add them together. 2 plus 3 is 5. So I'm going to call this d plus x. Okay, I think I can do this. Instead of opposite over adjacent, I need adjacent over opposite h. So cotangent of alpha is the adjacent side length, which is here in green, over the opposite, which is the height. Okay, not too bad. I'll do cotangent of beta in blue. Same definition, but this time some things have changed. We're now talking about beta. Cotangent is adjacent over opposite. The opposite is still h, but what's the adjacent this time? It's no longer all the green stuff. It's now just the x stuff. So the adjacent to the beta angle is simply x. All right. I'm going to substitute in my green stuff and my blue stuff into this equation and just see if maybe it makes any sense whatsoever. So they say h is equal to d over cotangent alpha, which I say is d plus x over h, minus cotangent beta, which I claim is x over h. You know, when I first saw this problem, I thought Mr. Simpson hated me. But you see that common denominator there? He really does love me. Okay, here we go. D over. The common denominator stays the same. It's h. D plus x minus x. The x's will cancel, leaving me with d. Excuse me. So d in the numerator position divided by the fraction d over h. How do you divide by fractions? A lot of people learn keep, change, flip. I want to multiply by h over h to get rid of the denominator. But I've shown that already, so I'll do a keep, change, flip for those of you who are more familiar with that. The keep, change, flip is just a cute little way to remember how to divide by fractions. And that is, you keep the numerator, you change the division problem into a multiplication problem, and then you flip, which reciprocate would be a better word, but you flip the denominator. So you keep, change, flip. That means instead of this problem, you have a whole new problem altogether, where you keep the numerator as d, you change the division into multiplication. So this is my k, this is my c, and then you flip the denominator h over d. And when you multiply straight across like this, the d in the numerator position and the d in the denominator position will reduce, leaving us with just h. So yes, we have shown that that equation is true. These two statements are equal. When I simplified the right-hand side of the equation, I got the left-hand side of the equation. For those of you who wanted to multiply by h over h, let's just do that real quick. Because the keep, change, flip is cute and fun and all, but I don't know if I would call that real math. So it's just kind of a cute way to remember how to divide by fractions. So I would say mathematically, the way we're supposed to do this is we want to eliminate the denominator. So if we multiply by h over h, That should do it. I'm just multiplying by a form of 1, but when I do the denominator, notice the h's will reduce, leaving me with just d in the denominator. Oh, and then the d's reduce, leaving us with just h. So yes, h equals h is a true statement. We have shown that it is true. Okay, I think I'm done. I will see you in the next video. Do your homework.